right? So yeah, can one of you tell me what a generator basically does? The common generators that we find in apartment buildings and all, what does it do? What do they do?
It gives us electricity when the electricity is not there.
Okay, correct. It generates electricity. Mm, like it generates electrical energy, you can say. But you know, energy cannot simply be created. Some other form of energy should be getting converted to electrical. So an AC generator converts what form of energy to electrical energy? Or what does it take to give you electricity?
Sir, is it mechanical? Because I think I've read that somewhere.
Okay, okay.
Mechanical to chemical.
Mechanical to chemical. No, no, no. It doesn't create chemical energy, no.
Oh yeah.
But tell me, what does a generator use to produce electrical energy? Do any of you know what is given to the generator to get electricity from it?
I'm not sure, sir.
We have to give it fuel. Okay, usually diesel. Okay, the common generators we use here in India, they are diesel based. Okay, so diesel has chemical energy stored in it. Fine, it undergoes combustion, and that chemical energy is converted to mechanical energy. Fine, actually I should say chemical energy is converted to heat energy first, gets converted to mechanical energy. Okay, there's an engine inside it, just like a vehicle engine. Vehicle engine is also is same, no? It generates like it uses or it consumes fuel. Okay, converts chemical energy to heat energy. Inside the engine, heat is generated, heat is converted to mechanical energy. That is what a vehicle engine does. Mechanical energy means it moves the vehicle forward. A generator takes it a step further. The mechanical energy generated is further converted to electrical energy in a generator. That is what it does. Okay, so this step is what we are going to discuss, how mechanical energy can be converted to electrical energy in an alternating current generator, AC generator. Okay, tell me the basic formula of Faraday's law. Faraday's law equation. Why are you all not answering to Faraday's law at all? He talks about induced EMF and it relates induced EMF to magnetic flux. So tell me the equation of Faraday.
It's flux by time. D
No,
phi by
tell properly.
d phi by dt.
Okay, induced EMF, okay, in a loop or coil is equal to rate of change of magnetic flux with respect to time. Okay, don't say flux by time. Okay, fine. So this is the idea that is used in an AC generator. There is a coil inside the generator and the flux through that coil is made to vary with time. And if you make flux through a coil vary with time, an EMF gets generated in the coil. And if you connect it to a circuit, it can drive current. Okay, that's the idea. Now, tell me, what are the different ways in which we can change the flux through a coil? How can magnetic flux through a coil be changed? What all can we do? Tell me the basic formula for magnetic flux.
Here we can change the current flowing around.
What current
Like
are
we
you
can,
talking about? Huh.
I mean, like we can increase it, increase the.
No, I didn't understand. Can you be, I mean, Can you put it in another way? My question is how to change magnetic flux through a coil. Or tell me the basic formula for magnetic flux. From that we can tell how it can be changed. Okay. Pradhin is saying we have to change the current. What current are you talking about? Is it current in that coil itself or in some other coil? And how does changing current change magnetic flux?
The
Okay.
flux formula
Okay.
is
Ha,
magnetic into area cos theta.
correct.
Area of the whole.
Flux is equal to, if the field is uniform and area vector is easy to write, then it is B dot A, which is B A cos theta. Correct, correct. So you can change magnetic field, you can change area, you can change the orientation between them, or you can do two or more of these also. You can change two or more of this. Any of them, any of these methods can be used to change flux. And some of you are saying current, that is also valid only. Maybe you're talking about self in terms of self-inductance. You know, self-inductance is magnetic flux divided by current. So if current changes, the magnetic flux through a coil changes. That's fine. But here in an AC generator, we are trying to produce current. There's no current. We are trying to produce it. So you should not say, I mean, yeah, in this context, you should not say that by varying current, we can vary flux. Okay. So yeah, we can change the magnetic field area or the orientation between them. In an AC generator, the idea used is the variation of orientation between the area vector and the magnetic field. So basically what you find in an AC generator is a coil which can rotate in a magnetic field. Nothing else is changed. We don't change the dimensions of the coil. So area is not changed. We don't change the magnetic field in which it rotates. So magnetic field also remains constant. But as you rotate the coil, the area vector of the coil keeps rotating and the orientation keeps changing. The angle between magnetic field and area vector keeps changing. So theta varies, cos theta varies, and the flux varies. That is what generates EMF in that coil. Okay, let me show you the schematic diagram. Just a moment. This is from your textbook itself. So in an AC generator, you find something like this. Now, as you can see, there is a north pole and a south pole here. These two belong to permanent magnets. So there are permanent magnets in an AC generator. What is their purpose? Their purpose is to produce a magnetic field. From north to south, you will have magnetic field like this inside the generator. Okay, everywhere between that north pole and south pole, there will be a field present. And as you can see, there is a coil. Okay, here like they have shown only one turn, but you can have n number of turns. Okay, you can imagine a coil wound like this, right? It will have its area vector obviously. In this present orientation, its area vector would be this way. Okay, vertically upward you can say. Assuming the coil is horizontal, area vector will be vertical. You know the area of a coil is perpendicular to the plane of the coil. So this is the area vector, and those green lines are the magnetic field lines. Okay, as the coil rotates, the angle between the area vector and the magnetic field keeps changing. Magnetic field doesn't change. Magnets are permanent and they are fixed. So the magnetic field does not change. The area vector keeps rotating inside that field. Okay. What makes or how do we make the coil rotate? That is where the mechanical energy gets used. Okay. The diesel that you give to the generator, it undergoes combustion, produces heat. How chemical energy is converted to heat energy, you will learn in chemistry. Okay. Then the heat that is produced rotates a shaft. Okay. So the shaft is connected to the coil. So the coil gets rotated by the heat. Okay. By the energy given by the heat, you can say. So heat to mechanical energy conversion that you have learnt in thermodynamics in 11th class. Okay. How to convert heat to mechanical energy or heat to work, heat engine. Now the mechanical energy, which is basically in the form of rotational kinetic energy of the coil and the shaft, that gets converted to electrical energy in a generator. So if this coil rotates at a constant rate omega, assume the coil rotates at a constant rate omega. Now how that constant rate is maintained and all is not part of the discussion here. You just assume that the heat generated somehow rotates the coil at a constant angular velocity omega. Now we know omega is rate of change of angle with respect to time d theta by dt by definition. Okay. Now the flux through this coil at any time is B A cos theta, right? B dot A B A cos theta. Now theta is a variable here because the coil is rotating with some angular velocity. If theta is a variable, flux becomes a variable. Therefore, the EMF induced in the coil, according to Faraday's law, minus d phi by dt, or you can just take the magnitude. Like for now, I'm writing the minus. Finally, if there's a negative sign also, we'll ignore. Okay, minus d phi b by dt. Differentiate this. B and A are constants. You'll only have to differentiate cos theta, but with respect to time. Can one of you tell me what is the derivative of cos theta with respect to time? What is the derivative of cos theta with respect to theta? Minus sin theta. Okay. But now we are differentiating with respect to time, which is some other variable. So this becomes BA cos theta derivative is minus sin theta, but that is when you differentiate it with respect to theta. Since you are differentiating with respect to time, you'll have to include a d theta by dt term. And d theta by dt, yeah, Pradyun, what you said is correct only. So d theta by dt by definition is nothing but omega, angular velocity. And there was a minus sign outside also, no? Minus minus cancel. But anyway, as I said, finally you'll have to get a, like you won't be writing that minus sign. So this effectively becomes BA omega sine theta, where theta is the angle at that instant. Now, by definition, omega is d theta by dt. That means d theta is equal to omega dt. Integrate both sides. Integral d theta becomes theta from initial angle to final angle is equal to omega is constant. How it is maintained constant? As I said, it's not part of the discussion now. And integral dt is time. So you get theta minus theta initial is omega t. Or you can say angle at any time is initial angle plus omega t. That's the angle between the area vector and magnetic field at any time. That we'll substitute here. Therefore, the induced EMF in the coil now becomes BA omega sine theta. In place of theta, we'll write initial angle plus omega into t. If initial angle is 0, between what and what? Between the area vector and the magnetic field. If initial angle is 0, you get induced EMF is equal to BA omega sine omega t. Now BA and omega are all constants and the maximum value of sine function is +1. When the sine function is maximum, the EMF will be maximum, right? So you can tell that the maximum EMF induced in that rotating coil will be BA omega into 1. So we will call this BA omega as E naught. That's the peak EMF that you can get. Okay. And therefore, the EMF in the coil can be expressed as E naught sine omega t. if initial angle is 0. If initial angle is non-zero, if theta initial is not 0, then the EMF induced in the coil becomes a more general expression, E naught sine omega t plus some initial angle, you can call it as phi naught. So this is the general equation for the EMF generated in an AC generator. Did you all understand how we are getting alternating, not alternating part we'll discuss. Did you all understand how we are getting a variable flux in the coil? How we derived the equation for the EMF? Rishi, is this clear?
Yes, sir.
Isha, did you understand the derivation?
Yes, sir.
Okay, fine. So simple idea. There are permanent magnets which create a magnetic field inside. And in that magnetic field, there's a coil present. Using the mechanical energy, we rotate the coil at a constant rate omega. When the coil rotates, the angle between the area vector and the magnetic field changes, thereby changing the flux. And if flux changes, you know there will be an EMF induced. Okay, that is what a generator produces. And you see, we got a sine function here. Now, sine function naturally, for some time it will be positive. After that, it will be negative. So this EMF that you get in the coil also, for some time it is positive and then it will be negative. Again, it will become positive and so on. Now you can see that this coil, the coil that you see here, is connected to, what do we call these? Terminals only, I should say. There's one terminal here. Okay. One side of the coil is connected to this, or one end of the coil is connected to this. And there's another terminal also, as you can see. This one. The other end of the coil is connected to this. Actually, I should not say connected also, it just touches. Now they have written the name there, slip rings. Okay. I'll tell you what it means. See, you will be rotating the coil continuously and EMF will get generated in the coil. But the coil will have two ends, no? Coil is nothing but a wire which is wound around itself many times, but it will have two ends. So you visualize something like this. Suppose this is one end. Okay, you wind it around as many times as you want. And let's say this is the other end. When this coil is rotated in a magnetic field, you will get an EMF between this point and this point. These 2 points should be connected to the circuit, okay, in which you want to drive the current. But see, imagine rotating the coil around this axis. When you do half a rotation, this blue point will go to that side and the orange point will have to come to this side. If it is free, they can move around. They can also rotate. But you imagine this connected to a circuit. Let's say there is a bulb or something in which you want to drive the current. Just a moment. Okay, in which you want to produce the current. If they are rigidly connected like this, the blue point and the orange point, and you rotate this coil now, won't the wire get twisted? Okay, are you all able to imagine that or not? It's like this point will come into contact with this point when you do half rotation. And when you keep rotating, these two will come into contact with each other. We should avoid that. So the coil should rotate, but the wire should not, I mean, this end of the wire and that end of the wire, they should not come into contact. So how they solve this problem is by using those slip rings. Imagine something like this. Assume this is the coil. This is the axis about which it rotates. Okay. You just imagine two rings. One ring here, conducting ring. It is connected to the circuit. There's another ring here that is also connected to the circuit. Okay. Now, one end of this coil, you make it touch this ring, just touch, it's not rigidly attached. So basically what happens as the coil rotates, this point of contact keeps sliding along this ring like this. It keeps going around. Fine. So that orange wire that I am showing here is not rigidly connected to the slip ring. It's connected to the coil, yes. Okay. If the coil rotates, the orange wire comes to the left side, but it's not rigidly connected to the ring. So on the ring, it just slides to the left side. And then you imagine the other terminal, other end of the coil, make it pass through this ring. It doesn't touch this ring. Okay. It's, I mean, the radius is adjusted that way. It doesn't touch this ring, but it touches the other ring. Just a moment. A smaller ring here. The upper ring is a bigger ring and the lower ring is a smaller one. So that blue wire which passes through the upper ring without touching it comes down and touches the lower ring. Now you imagine the coil rotating like this. What will happen? The orange wire will keep rotating and touching the upper slip ring. The blue wire will keep rotating and it will keep touching the lower slip ring like this. Okay. Orange one rotates in this circle. Blue one rotates in that circle. So they are not permanently attached or they are not rigidly fixed to those rings. Now, even if the loop rotates, there won't be any twisting of wire. The blue wire will never touch the orange wire. Is this clear? Are you all able to imagine what is happening? Isha, Pradyun, Rishi, is the idea clear?
Yes, sir.
In sometimes they use carbon brushes also. Carbon is a conductor. So they make the wire touch the slip ring through carbon brushes. Okay, such that there are more points of contact. And then this can be connected to the circuit, bulb or whatever it is, whatever load you want to supply current to. Fine. So that is what happens in an AC generator. But remember this equation and the derivation, how this equation is derived. How much is E naught here? E naught here is B A omega. It depends on how fast you rotate the coil. Okay. Same concept is used in what are they called? I'm not able to collect the name. Like in bicycles, the light, the electric bell and all. When you ride the bicycle, it gets, I mean, electricity gets generated this way. When you ride the bicycle, it's called a dynamo. Yeah. Dynamo is like a mini generator. Fine. When you ride the bicycle, the mechanical energy that you are supplying, okay, the energy inside your body is getting converted to mechanical energy. That's how the cycle is moving forward. The wheel is rotating. Some of that energy rotates the dynamo, rotates the coil inside the dynamo, and it is able to light up the whatever headlamp or provide electricity to the bell or whatever digital things you are using. Okay, so dynamo is like a mini generator, small version of a generator. And why do we call this an alternating EMF? Because it varies sinusoidally with time. For some time, this function will be positive, and for some time, this function will be negative. Means for some time, the orange side will be positive, higher potential. The blue side will be at lower potential. But when the other half of the rotation is happening, the orange side will be at lower potential, the blue side will be at higher potential. So for some time, okay, just a moment. When orange is at high potential and blue is at low potential, current will go this way through the bulb. When orange is at low potential and blue is at high potential, okay, then current will flow the other way. It keeps changing direction. For some time it flows clockwise, for some time it flows anti-clockwise. That is why that current is called alternating current, AC. Okay, and EMF also keeps changing its direction. No, polarity keeps changing. we call it as alternating EMF. Okay. So remember, the general equation for alternating EMF is E is equal to E naught sine omega t plus phi. You can write cos also, nothing wrong in that. Because sine function can be converted to a cos function just by changing the constant inside. You add a plus pi by 2 or you subtract a pi by 2, it changes to cos. Not a big deal. Okay, but these conversions and all we'll discuss in detail in the next chapter, alternating current. Okay, so that is how an AC generator works. Any doubts in this? Fine.
Sir, can you
Yeah.
show the last part of the derivation?
Last part, this one.
A bit more up, sir. Yeah, sir, this part.
Okay.
Yeah, sir.
Okay, fine. Next, one thing we didn't discuss about is eddy currents. Any idea what these are? What is eddy current? Okay,
No idea, sir.
fine. So see, you can say these are just random currents with no particular direction of flow. Okay, there's no well-defined path in which the current flows. So there is a certain region in which currents flow randomly. That is what you call as eddy current. Okay. Now, how are these generated? We know that if magnetic field in a region changes, okay, not flux, if field varies, induced electric field is produced. That is one thing. And in general, if magnetic flux varies, or okay, wait, if a conductor moves in a magnetic field, charge separation will occur. Okay, why? Because of that magnetic force F is equal to QV cross B. That is how motional EMF is generated. If a conductor moves in a magnetic field, charges move around in the conductor. Okay. So any of these methods can be used to generate eddy currents. Now, till now in this chapter, whenever we discussed motional EMF or induced EMF current flowing in a circuit and all, we considered circuits which had well-defined path for current flow. For example, we had solved a question like this. Okay, this rod moves, there is a magnetic field, EMF gets generated. If you know the resistance, how much is the current? Okay, because here there is a well-defined path for the current to flow. So we call that as normal current, right? Even when we talked about induced electric field, we took something like this. We took a circular loop and we assumed there is a magnetic field which varies with time. If field varies with time, flux varies with time, that generates an EMF. And here also, the circular loop is the only path in which the current can flow. There is a well-defined path for it to flow. Okay. Now you consider something like this. Let's say there is a random plate, two-dimensional system. Just a moment. Okay, conducting plate. Okay. Imagine there is a magnetic field into the plane of the screen. And assume it varies with time. What does a time varying magnetic field produce? What does a time varying magnetic field produce? You have to answer.
Sir, an electric field.
Induced electric field. It produces
Yeah,
induced
yes, sir.
electric field. Yeah, I got one answer as flux. See, any magnetic field produces flux. It doesn't have to vary. Okay, but if field varies, flux varies, and it gives rise to an induced EMF. Correct. Okay, and we discussed this point also. Induced EMF or the induced, not EMF, electric field. Induced electric field will be in a plane perpendicular to the time varying magnetic field. Now this magnetic field is into the screen, means it's in the Z direction. The plane perpendicular to Z direction is the XY plane. That is the plane of your screen. So induced electric field will be in the plane of your screen. And induced electric field lines form closed loops. We know that. So as a result, what happens in this plate, charges will start moving around everywhere because induced electric field is produced everywhere, right? So electrons everywhere will start moving. So randomly you will see currents flowing at different points of this, okay? Or you can say at all points of this conductor. There's no well-defined path for the charges to flow. This current is what you call as eddy current. Okay. And there's another way also to generate eddy current. Again, consider a random plate. Assume there is a region in which a magnetic field is present. Now you take this plate. This plate is initially out of the magnetic field. When it is out of the magnetic field, there's no flux, there is no motional EMF, nothing. Make this plate move through the magnetic field now. As it enters into the magnetic field, okay, clearly it's a case of a conductor moving inside a magnetic field. Velocity is to the right. Velocity is to the right, magnetic field is inward, then V cross B will be upward. So positive charges will go up, negative charges will go down. But that happens everywhere now in this plate. So as a result, you will see random currents flowing. There's no well-defined path for the charges to move. So you'll see currents flowing randomly at different points like this. Okay, that also generates eddy currents. You just make a conductor move in a magnetic field, not conductor. It depends on the shape of the conductor. You make a lump of conductor move in a magnetic field, you will get eddy currents. Okay, so basically a conductor in which there is no well-defined path for the charge to flow can give rise to eddy currents. And in that itself, you can find a way to reduce eddy currents. You have to prevent the ability to generate these random currents. So if you want to reduce eddy currents, the actual method they use is that they produce or they make grooves inside the conductor. Okay. The more grooves you make, the more well-defined paths you will be providing for the charge to flow. Okay. See, if you make a groove like this, now the charge cannot go in this direction. It can't go from one side of the groove to the other side because in between there's no conductor. So you are preventing some eddy currents. You are reducing the eddy currents. So one way to reduce eddy currents in a conductor is to make grooves in the conductor. Okay, create gaps. Don't allow charges to flow randomly. Obvious answer. Okay. Now, how are these used or what is the benefit of this? See, there's an obvious disadvantage of eddy currents. One of you tell me, when current flows through a conductor, what happens? What is generated? When current flows through a conductor, what is generated?
Sir, heat.
Heat, correct. Okay. Now, you may call it an advantage, you may call it a disadvantage. If heat generation is what you want, then eddy current is an advantage, because eddy currents are basically currents flowing everywhere in the conductor. They produce a lot of heat. That conductor will heat up. So if heat generation is your intention, then eddy current is a good thing. But suppose heat generation is not the purpose here, we don't want the conductor to get heated, then eddy current becomes a bad thing. There you will have to find ways to reduce eddy currents. Okay, this is the principle used in an induction stove. Okay, do any of you know how it works, induction stove? Okay, have any of you used or seen induction stoves being used?
Yes, sir.
Okay, uh, see, you must be aware, if you have seen an induction stove being used, you must be aware that not all vessels can be used on an induction stove. Okay, it has to be induction compatible. So basically what happens in the induction stove is there will be a coil. You assume this is the stove. Okay, side view. The controls and all will be there, that's fine. But inside the coil, inside the stove, there is a coil. Okay, okay. Like this. The stove will be connected to the power supply. Now, when you connect it to the power supply, the usual current that we get in a household circuit is alternating current. It keeps changing its direction. So if the current flowing through this coil is an alternating current, alternating, the name itself suggests that it keeps changing direction, forward, backward, forward. So it's a variable current. When current passes through a coil, you know a magnetic field will get generated. So imagine these field lines produced by this coil. Okay. In which direction exactly the field gets produced depends on the exact direction in which the current flows. Let it be, but a field does get generated like this. Assume at an instant, the field is pointed in the upward direction roughly. Now, if it's a constant current, the magnetic field will also be constant. But if the current is variable, the magnetic field will be variable. So you are producing a magnetic field which varies with time. Okay, or that is what happens in the induction stove. Now, when you put a conducting plate on it, okay, yeah, just a moment. You put a conducting plate on it. What will happen? That plate now, that conducting plate is in the presence of a time varying magnetic field. If a conducting plate is in the presence of a time varying magnetic field, you will see eddy currents generated in it. All over that plate, eddy currents will get generated. Okay. And those eddy currents, what they do, they heat up the conducting plate, and that in turn heats up the food that is on the plate. Fine. And see, it depends. Not every conductor can produce the same amount of heat. In insulators, you won't get eddy current at all, because in insulator, even if you put it on, even if you put it in the presence of a time varying magnetic field, the induced electric field won't be able to drive electrons. In insulators, there are no conduction electrons. Okay. So heat won't get produced. That's why if you put an insulator on an induction stove, it won't work. Okay. Like it won't get heated. Even if you switch on the stove, it's not going to get heated. Okay. So some materials are highly compatible with this. They can produce a lot of heat from eddy currents. Such materials are the ones with which you should make utensils which are induction compatible. Okay, but remember the idea behind the working of an induction stove is this only. induced EMF, induced electric field actually, induced electric field and eddy currents. Okay, so in the base of that induction vessel that is there, eddy currents are generated, which heats up the base, and that in turn heats up the wood or whatever you put on it. Okay, did you understand? Any doubt in this? How much heat you want and all depends, as you know, depends on how rapidly the magnetic field varies. So the controls on the induction stove must have been changing the flow of current or something such that the magnetic field changes and the eddy current changes, thereby changing the amount of heat that is generated. Okay. So if heat generation is what you want, eddy current is a good thing. If heat generation is not what you want, then eddy current is a bad thing. Right? But actually, eddy currents are a very effective way to, or okay, I should say, eddy currents are an effective way to stop moving conductors. Okay, in fact, these are used in magnetic braking also. Brakes. Okay, for example, you consider the wheels of a moving vehicle. Assume they are made of conducting material. Fine. Especially, you must have heard of maglev trains. Have any of you heard of this? I think in Japan they use these trains, maglev. It is short for magnetic levitation. Okay. So the wheel of the train won't be touching the track at all. Okay. The wheels are magnetic, the track is magnetic. The wheel will be floating on the track. And the train moves forward very smoothly, almost with zero friction. Because if there's no rubbing between surfaces, there won't be friction. Air resistance will be there, but this mechanical friction won't be, I mean, solid friction won't be there. So maglev trains are able to move very fast. Okay. Bullet trains, that is the technology they use. Now, if you want to stop such a train without friction, how can you stop the train? That is difficult. Okay. So there they use something called magnetic braking. So the wheels, which are made of conducting material, no, if you want to stop the train, a magnetic field gets generated from the tracks or whatever. Exact mechanism I don't know. Okay. But then what happens is something like this. Let's say this is part of the wheel. Fine. You generate a magnetic field. Mostly in the tracks itself, it has to get generated. So there should be some kind of signaling possible. So in the tracks, a magnetic field gets generated and the wheel moves through that magnetic field. What happens? The kinetic energy, see, the speed with which the wheel is moving, this speed itself is the reason for the motional EMF. That is what generates eddy currents, right? So when a conductor moves like this in a magnetic field, motional EMF is generated or eddy currents are generated, right? Eddy currents means electrical energy is generated, which further gets converted to heat energy. But where is all that energy coming from? It all comes from this kinetic energy only. Okay. So when this conductor moving with a speed v enters into a magnetic field, or let's say it moves inside a magnetic field, the kinetic energy which is there with the conductor gets converted to electrical energy of the eddy currents, which further gets converted to heat and it is dissipated. So kinetic energy is getting used up and released as heat. If kinetic energy is getting used up, it means the speed is reducing. That is how magnetic braking works. Okay. I'll send you some links to some YouTube videos also where you will be able to see. Okay. This is I mean, this is not negligible. This effect is not negligible. When a fast moving conductor enters into a magnetic field or a fast moving conductor is already inside a magnetic field, if you don't keep pushing it, it will slow down and stop because of eddy currents. Because kinetic energy gets converted to electrical energy and gets converted to heat energy, the object will stop. Okay. You can do an experiment also. I'll see if it is possible with simple things. If you can do the experiment, I'll suggest. I'll find out and tell you. But did you understand how magnetic braking works? And this does not require contact of the conductor with anything. Just move inside a magnetic field, it will slow down. It doesn't have to touch anything. Fine. So that is what we call as magnetic braking. So here eddy currents are used to an advantage. Okay, we use it to slow down the object. Okay, any doubts? AC generator, eddy currents.
No, sir.
And did we miss anything in the chapter? See, we started from Faraday's law, talked about Lenz's law, solved some basic questions. Then we discussed how a time varying magnetic flux generates EMF. There are two ways. One is motional EMF, when conductor moves inside a magnetic field, BLV or B dot L cross V. We discussed all that in detail. Another way to generate EMF is by varying the magnetic field. A time varying magnetic field automatically produces an electric field, induced electric field. We discussed properties of induced electric fields. Okay, we solved problems based on that. We derived induced electric field in one case. Then we talked about inductance, self-inductance, mutual inductance, properties of inductor, what to do if an inductor is present in a circuit, what does it behave like initially, finally, how to write induced EMF across an inductor, minus L di by dt, energy stored in an inductor. Okay, yeah, this reminds me of one thing. One thing we didn't derive is the energy density in a magnetic field. Energy density, that is energy per unit volume. In an electric field, we had derived this when we talked about energy stored in a capacitor. It is half epsilon naught E square. Electric field has energy in it, and this is the energy per unit volume present in an electric field E. Similarly, magnetic field also stores energy, and you can derive the expression for energy per unit volume in a magnetic field. Okay, let us do that. And see, to derive the energy per unit volume, you can consider a system which produces a uniform field. Like when deriving half epsilon naught E square, we used a parallel plate capacitor. Why? Between the plates of a parallel plate capacitor, you have a uniform electric field. And you know the energy stored in a parallel plate capacitor. So that energy should be present in that uniform electric field. Then we could easily find out how much energy is stored per unit volume in that field. We will use a similar idea to derive energy density in a magnetic field also. One of you tell me a system which produces a uniform magnetic field. What kind of coil produces a uniform magnetic field? Isha, which coil produces a uniform magnetic field? Rishi, how to get a uniform magnetic field?
Sir, using a cylindrical coil.
What is a cylindrical coil?
Like
Solenoid.
yeah, that one.
Okay. Long solenoid produces a uniform magnetic field mu naught Ni. For most part of the solenoid, it will be uniform. At the edges, you may see a slight variation in the field, but we'll ignore that. Long solenoid, no, so almost uniform throughout. So consider a long solenoid. Let's say a current I passes through it. Then the magnetic field produced will be mu naught Ni. N is the number of turns per unit length. Let's say L is the length of the solenoid, R is its radius. Can one of you tell me what is the formula for self-inductance of a long solenoid? We derived self-inductance only for solenoids. What is the expression we derived?
Sir, mu naught
Hmm,
n square L pi r square.
correct. Mu naught n square L pi r square depends on the medium and geometrical factors. This is the self-inductance of a solenoid. Okay. Now tell me, what is the formula for energy stored in an inductor? Okay. it is half L I square. So when a current I flows through the inductor, the energy stored in it is half L I square, where L is the self-inductance of that coil inductor. Fine. So in a solenoid, having n number of turns per unit length, length L and radius R, if a current I flows, then energy stored in the solenoid becomes half L of a solenoid is mu naught n square L pi R square into I square. This is the energy stored in the solenoid. And in what form is this stored? This is magnetic energy. And where is this stored? It is the magnetic energy stored in the magnetic field of the solenoid. Inside the solenoid, there are field lines, no? In that field, it is stored. Okay. So we know how much energy is there in the magnetic field of the solenoid. And we also know in what space that magnetic field is present. One of you tell me, how do you express the volume of a solenoid? You said cylindrical, that is the hint. How do you express volume of a solenoid?
Sir, pi r square h is the formula for volume
Pi r
cylinder.
square h is the formula for volume of a cylinder. In this case, in case of a solenoid, we don't call it h, we call it as L, length of the solenoid. Okay, just a moment. Okay, we can use the diagram that we used a few days back. Okay, let's consider this one. So all this energy, half L I square that is there, it's stored in the magnetic field produced by the solenoid, and that magnetic field is in this volume, inside the solenoid, cylindrical volume of the solenoid. Right? We know the radius is R and the length is L. So pi R square L will be the volume. Okay. We know how much energy is stored in that volume, and we know how much is the volume. Therefore, we can now write energy stored per unit volume. Divide these two. Half mu naught n square L pi R square into I square divided by volume pi R square L. Okay. Pi R square L cancels. What will you be left with? Mu naught n square I square divided by 2. That is the energy per unit volume in a solenoid. Now our aim was to derive energy per unit volume, that is energy density in magnetic field, not specific to a solenoid. So we have to express this in terms of the magnetic field. Now we know magnetic field produced by the solenoid is mu naught Ni. When you square this, you get mu naught square n square I square. So you can say that b square divided by mu naught. Okay, send one mu naught to the left hand side. The other mu naught will be there. N square I square will be there. And that is what you see here. So this can be replaced by b square by mu naught. And what you will finally get is that the energy per unit volume in a magnetic field B is b square by 2 mu naught. Okay, we derived this result using a solenoid because in a solenoid uniform magnetic field is produced. It's easy to write the volume and all, but the result is true in general. Anywhere, if a magnetic field B is present, the energy per unit volume in that field B is b square by 2 mu naught. And the formula is very similar to energy density in electric field. For electric field, we have half epsilon naught E square. Okay. Now in electrostatics or electricity, wherever you have epsilon naught, in magnetism, you get 1 by mu naught. So this changes to half. In place of epsilon naught, you write 1 by mu naught. Electric field gets replaced by magnetic field. And this is the expression that you have here. Okay, so that's the energy density in a magnetic field b square by 2 mu naught. We'll be using this in electromagnetic waves. Okay, you know waves transfer energy, right? So how much energy or what is the intensity of electromagnetic waves in that derivation, we'll be using this. Okay? And they can ask you direct questions also. They can give you a field and ask what is the energy density, or they can say a certain region is filled with a magnetic field. How much is the energy in that region? Now, if you know energy per unit volume, multiply with volume, you'll get energy. Okay, that way. Fine. Let's solve one question based on this. Now, direct questions you can solve it. Constant field is given. You can easily tell what is the energy, or uniform field is given. You can easily tell what is the energy. Let's take a non-uniform magnetic field. Assume there's a magnetic field given by 2 root x square plus y square. In many of the worksheet questions that I'm sending you also, I'm using a field like this. Okay, I don't know if you're solving those sheets or not. Let's say there's a magnetic field 2 root x square plus y square, and its direction is k cap. Okay. Uh, all of your MPC students only, so you must be knowing what does square root of x square plus y square give you in 3D geometry? It gives the distance. Pradyun, your answer is correct. It gives the distance of a point from the z-axis. Okay. So root of x square plus y square, you can call it as r if you want, where r is the distance from the z-axis. So basically this magnetic field is a field which varies with distance from the z-axis. So you can think of it like this. Okay. And from point to point, as you move away from the z-axis, from point to point, the field strength increases. So it's a non-uniform magnetic field. Now I want you all to find out, due to this magnetic field, what is the energy? U stands for energy. Energy stored in a cylinder of radius, let's say 2 meters, and length. Okay, length also should be given because we need to know the volume. Radius 2 meters and length, let's say 10 meters. Whose axis, the cylinder's axis, coincides with the z-axis. Okay, I want you all to find out the amount of energy stored in this cylinder. Try, give it a try, we'll see. And I'll help you in visualization. Just let me copy this magnetic field equation. Due to this magnetic field, we need to find out how much energy is stored in this cylindrical space. If you want to start solving on your own, you can. Assume this is the cylinder. This is its axis. The axis is the z-axis. These points are inside the cylinder. Okay. Now, how is this magnetic field? It depends on the distance from the z-axis. The axis of the cylinder coincides with the z-axis, right? And the direction of the magnetic field is the z direction itself. And you can see that the magnetic field is proportional to distance from z-axis. So as the distance increases, the field increases. So you can imagine the field lines like this. Just a moment. At a fixed distance from the axis, you will have a fixed amount of magnetic field. So I'm considering an imaginary ring of a certain radius around this axis. At that distance, depending on the distance, you will have one or a certain amount of magnetic field present. And the field is in the z direction, means it's parallel to the axis of the cylinder. So these are the magnetic field lines. I have to draw long lines actually, but that's fine. You can understand. Right. That depends on the strength of the magnetic field there. Now, if you consider a slightly larger ring, means slightly greater distance from the axis. And if distance from the axis increases, you know the field strength increases according to the equation of the field. So at those points, okay, at points of that other ring, you can say the field will be stronger. So at different distances from the axis of the cylinder, you have different amounts of magnetic field present. Situation is like that. Can you all tell me an idea? Field is not uniform. Now you know the formula for energy density in a magnetic field. Energy per unit volume is B square by 2 mu naught. Had the field been same everywhere, you could have said that the energy density is same everywhere. So I'll take that energy density and multiply with volume. I'll get the field directly. Sorry, I'll get the energy, total energy directly. You could have done that. But here, the field is not uniform. What can be done? Can you identify a section or a region where the field will be uniform? Can you think of a volume in which the magnetic field will be uniform in this case? Tell me, on what factors does the magnetic field depend in this question? On what factor does the magnetic field in this question depend? From the equation of magnetic field, you tell. Based on what does the field change from point to point?
Exert the current.
Where is current in that magnetic field equation?
Oh.
It depends on the distance from the z-axis. Okay, the magnetic field equation is given to you. In that equation, you can see that the magnetic field depends on distance from z-axis. So if you consider a fixed distance from the z-axis, then magnetic field will be uniform. And if field is uniform, you can use this formula to find out the energy in that volume. If you can identify a volume over which the field is uniform, then you use this formula and multiply with the volume, you will get the energy. Energy per unit volume is this much. That means energy is B square by 2 mu naught multiplied with that volume over which the field is B. Okay. And here, according to the equation, the magnetic field varies with distance from the z-axis. So what we are going to do is, we are going to consider a volume which is equidistant from the z-axis. Okay, just to make visualization easy, I'm going to broaden the cylinder. That's the original cylinder that we considered. Consider something like this now. Okay, just a moment. We need to consider a volume which is at a fixed distance from the z-axis. And that volume is going to look like this. So you have to imagine a thick hollow cylinder. This way. Its axis is also the z-axis itself. Consider this thick hollow cylinder. Assume its radius is small r and its thickness is dr. Now we know magnetic field varies from distance to distance from the axis of the actual cylinder. Now this is a thin, okay, what do you call, thin walled hollow cylinder that we have considered. Then for this distance r, at all points inside this thin wall, you can assume the field is uniform. From this cylinder to the next hollow cylinder, the field could change. But in the wall of this hollow cylinder, the field is uniform. Do you all agree with this or not? Isha, is the picture clear? Are you able to visualize what is happening?
Yes, sir.
Rishi, what about you? Did you understand how field in the wall of this hollow cylinder becomes uniform?
Yes, sir.
So you can visualize on the base. The field increases as you move away from the axis of the main cylinder. It becomes stronger and stronger as you move away from the axis. The hollow cylinder that we have considered has all its points at a fixed distance from the axis of the main cylinder. So all the points on the wall of this hollow cylinder will be under the influence of a uniform magnetic field. And luckily, the magnetic field given to you in the problem is 2 root x square plus y square. No, it is like 2r. So we know the magnetic field at a distance r. That means this is the magnetic field in the wall of the hollow cylinder that we considered. Hollow cylinder, yeah. Okay. Now we have to write, or we have to derive an expression for the volume in the wall of that hollow cylinder. Because this uniform magnetic field will be present in that volume. So we have to derive an expression for this volume now. Any idea how to express that volume? It's a hollow cylinder whose thickness is dr, radius is r. How to write the volume in that thickness?
Here we have to find the volume of the hollow part. Will be the bigger radius minus the smaller radius and the normal
Okay, so
formula.
you are saying we'll do the outer volume minus the inner volume.
Yes, sir.
See, that is the general way to do it. But see, by now you should have been comfortable with all this. Okay, I'm sure you all remember what to do. You are not able to recollect. Suppose there is a disk plate. Okay. Now you know a disk is a collection of rings. Now if you consider a ring on this disk. Now disk is an areal distribution. Okay. Assume this is a disk of charge. So it has charge distributed all over the area. But you have to find out how much charge is there only on this ring element. Ring's radius is r and ring's thickness is dr. How do you write the area of the ring element? Do any of you remember? You don't always do outer area minus inner area. Okay, these are basic things you should remember. Anyway, okay, we have another 10 minutes. So let me derive. Listen, all of you. The inner radius is r, outer radius is r plus dr. Now we want that area, that white area that is there. So it's the outer circle's area minus the inner circle's area, right? One of you quickly tell me, how do you write area of the outer circle here? Outer circle radius is r plus dr. How do you write its area? Isha, what is the formula for area of a circle?
So pi r square.
So if the radius is r plus dr, then the area becomes pi r plus
Pi
dr
plus.
whole square. That is the outer circle's area. Minus inner circle's radius is r. So its area will be pi r square simply. Okay. Pi common. A plus b whole square. A square plus b square plus 2ab. Okay. Minus this r square is there. We have taken pi common. Now the r square term gets cancelled. What will you be left with? Pi into 2r dr plus dr whole square. Now compared to dr whole square will be negligibly small. Okay, because dr itself is a small term, 0.0000 something 1. And when you square it, you will get again those many zeros. Okay, so compared to dr square is negligible. So we'll ignore this term. And if you ignore this term, what will you be left with? You will be left with, send the pi inside. You will be left with 2 pi r dr. Okay, we use this in derivation of electric field produced by a disk also. Okay, some of you were not there at that time. Now visualize what 2 pi r dr means for this ring. Two pi r, just a moment. 2 pi r is this circumference. Okay, and dr is the thickness. So 2 pi r dr is simply the circumference multiplied with the thickness. And what is it giving us? Area. Is this clear to all of you? Any doubt in this? So if you want the area of that thin ring element, you don't always do outer area minus inner area. You just do The length of that element multiplied with its width. Length multiplied with width gives you the area. Now come back to the question that we were solving. We want the volume of that thin-walled cylinder. Inside that thin wall, we need to know what is the volume. Now you all said outer volume minus inner volume. We don't do that. Okay. What we do is we take the area of this cylinder. What area? The surface area, curved surface area. Okay. Of this cylinder. And we multiplied with the thickness of multiply it with the thickness of the wall. That's all. If you do outer volume minus inner volume also, you'll get the same result. But since the thickness is very less, dr, okay, infinitesimal thickness, you can just do area multiplied with thickness to get the volume. Did you all understand the idea? Will you tell this if I ask you the next time?
Yes, sir.
Okay. For thin regions, this is how you find out areas, volumes and all. If it's volume, area multiplied with the small thickness. If it's area that you want, like a ring element's area, length multiplied with the small width, that will give you the area. Okay. And I'm sure you all must have used this a lot of times. Right from, where do you start using this in 11th class? You start using it in center of mass. Yeah. Deriving the center of mass of a semicircular disk, hemisphere, solid hemisphere, hollow hemisphere. There you will use these. Okay, anyway. So the volume now, small volume in the thickness of the wall can be expressed as, tell me what is the curved surface area of a cylinder?
Two pi RH.
2 pi r multiplied with L. Okay, length of the cylinder. 2 pi r is that circumference multiplied with the length gives you the curved surface area. So 2 pi small r into L. Thickness is dr. That is the volume in the wall of this cylinder. And in this volume, there is a magnetic field of 2r present. 2 root x square plus y square means 2r. Okay. So the magnetic field present is 2r. The volume is 2 pi r L dr. Now we know energy per unit volume, du by dvl, right, is equal to b square by 2 mu naught. That means the small energy present in a small volume will be b square by 2 mu naught into dv, that small volume. Okay, b square here becomes 2r whole square, which is 4r square, divided by 2 mu naught, and that small volume is 2 pi r L dr. So that is the amount of energy, magnetic energy present in that thin hollow cylinder. Okay. And the original cylinder, which is there was no cylinder actually. You were given a space and you were asked to find out how much energy is in that space. That space was in the form of a full cylinder. Okay. Now, since that space consisted a magnetic field which varies with distance from the axis, we are splitting that space into smaller spaces, hollow cylinders. Okay, or hollow cylindrical spaces. Fine. So the original space that was given to you is a collection of these hollow cylindrical spaces. So you have to find out the energy in one hollow cylindrical space and you integrate it with proper limits. What are the proper limits? Radius 0 to, what is the radius of the cylindrical area given to you? 2 meters. So small r should vary from 0 to 2 meters. If you integrate properly, you'll get the total energy in that space. So let's complete it. 4r square by 2 mu naught, 1, 2 gets, okay, 2's will get cancelled anyway. So the small amount of energy present in the wall of that thin hollow cylinder is 4 pi L by mu naught r cube dr. And if you want total energy, you integrate this with the limit 0 to 2. That's all. Okay, so we just applied the formula of energy density of a magnetic field, but we took a slightly difficult case where the magnetic field is a non-uniform one. If field was uniform throughout the volume, directly you would have gotten the answer. energy by volume is B square by 2 mu naught. Substitute that uniform field here, send the volume to the other side, you will get energy. Okay, if field is non-uniform, then there arises a difficulty. In case of non-uniform field, you will have to identify small volumes where the field is uniform. Like in this case, we first visualized what the field is varying depending on, and we found that field varies depending on the distance from the axis. That was given in the question. So from one distance to one distance, the field was varying. So we took a certain volume at a fixed distance from the axis, and that became a hollow cylinder's wall. We wrote an expression for that volume. We wrote an expression for energy in that volume. Integrating that, we got the total energy in the entire cylindrical space. Okay, I'll send you some more questions like this in the worksheet. In the last worksheets also, the ones based on magnetic flux and all, you were given non-uniform fields like this. Try to solve those questions. Okay, that is all there is in this chapter. Practice a few problems. And Saturday, we'll start the next chapter, alternating current. Fine. Thank you all. We'll continue on Saturday.
Thank you, sir. Sir, also can you send today's notes?
Okay. Yeah, I'll send.
Thank you.